Yeah, thanks very much. It's a great pleasure to give this presentation, to provide this presentation to CentrEau, and it's also a pleasure. Well, I don't see you, but I saw a number of people passing by. So yeah, it's a great pleasure for me to give this presentation about a topic that's really dominated my well, let's say the last 7 or 8 years of my work at Delft University. It's about water and industry. So more specifically, I'll focus on treatment technologies, but also introduce what exactly is water and industry about. So let's go to the next slide and let's see how I do this. Yeah. So I thought, well, let's ask ChatGPT to ask about industry and water. And then I got this response. So a relationship between industry and water is a complex one. It's also an essential resource, the water, and it's used for a variety of purposes. And this includes a couple of processes, including cooling and cleaning and so on. But also it says that, if these industrial activities using water, they have a significant impact on water resources. So nothing wrong about that, but that's more or less what we already know, of course. So it's not new, but yeah, it's a kind of relief that this is more or less correct for me. So let's move on to water demand. So what exactly is this? And here you see a picture. It's an old picture, and it appears, as far as I know, well, I checked last time a couple of years ago in the World Almanac, and it's pretty constant. It always says that globally, agriculture has a water demand of 70% of the total water demand, and industry is 20%, and households is 10%. What's changing slowly? That's the share of the water demand in Europe, which is now increasing to almost 60%. So it depends very much on the area. But if we speak about demand, what is it exactly? Is it abstraction from natural sources? Is it the use of the water? Or is it the consumption of water? This is really not clear. So in many statistics, you won't find an answer to this question. And that's why, it's a bit complicated to talk about these numbers. But let's first focus a bit on the industry. What exactly is the industry? And this is one way looking at the industry. It's based on the NACA. I don't know if you know this, but that's a European classification, nomenclature statistique des activités économiques. That's a classification of industries. And we have, for example, agriculture and fisheries, and we have tourism, and that's also considered industry. We have a financial industry. This includes data centers, and but also we have mining and manufacturing, and especially manufacturing. That's my focus. So manufacturing industry that focuses on the production of goods and services, but also sometimes when we speak about, for example, the paper industry, it also includes the group of manufacturers or the businesses related to paper. Most importantly, when we speak about manufacturing industry, we focus on the production itself, which contains the water intensive aspects, the processes. And sometimes we also speak about primary, secondary, and tertiary industries. And the primary, obviously, that's agriculture and fisheries, but also mining. Secondary, that's the production industry, and tertiary, that's tourism, services, and so on. But this is not very clear-cut distinction. So this is an old school picture showing a very early, it was, if I'm not mistaken, in the 1600s, a paper mill in the well, the only natural park in the Netherlands, the Veluwe. And so why are these paper mills here at this place? And there are three reasons, in fact. We have creeks, there's flowing water, so this can drive water mills. Secondly, there's water available, obviously, and third, the water is soft. So that was the main reason why so many paper mills emerged in the Veluwe area. It's good to know, well, we all know the Industrial Revolution, which started with the use of water power and steam power. And water power, that's the upper, so what we call a water mill, to drive industrial processes. In that time, it was important that water was available. The quality was less important. Later on, we moved to the use of steam. And then, of course, water availability is important, but also the quality. This as an example, another early industry is the textile industry, where especially steam was used a lot in the beginning. And this is a picture showing a cotton mill, and it was steam powered, very mechanized. But also the textile industry was one of the first that really caused environmental problems. And the main reason was the use of all those nice colors that ended up for a big part in the residual or wastewater. So when we speak about industries like paper and textile industry, we call them water intensive industries. And what is a definition? So this is related to water demand, but as mentioned, it's a difficult definition. What exactly is demand? Is it withdrawal? Is it the extraction effect of the water? Is it the use of water? Do these industries need a lot of water, or do they consume a lot of water? So when the water is used up, in fact, when it disappears, or is it related to water production? And we can use all definitions, in fact. So an example, a paper factory, a paper mill, uses a lot of water. But if a lot of water is reused, which is becoming more practice in the paper industry, then of course it's not consumed. The water consumption is not high. So in terms of water use, you might call it water intensive, but in terms of water consumption, it's less intensive. So it's all related to looking at this picture. So we have an intake, which is the withdrawal or any source of water. It's used in the company. And then we have a product which might contain water. But also there's some residual water and there's a loss of water, for example, as vapor. So when we speak about intensity, it depends on what definition of water demand we use and what industrial sector we're looking at. This is an example of a water-intensive industry, and when we look at the left picture, the water consumption is expressed in terms of volume per dollar output. Well, and then what we see is that apparently paint and coating manufacturing, this is in the United States, has a very high water volume use per dollar output, and other industries are less. But yeah, if we look at this picture, the right picture, we see that the chemical industry, the pulp and paper industry are very water intensive. But this is based on the volume of wastewater produced. So again, this makes clear that it's difficult to define what exactly is a water intensive industry. And it's much related to what water quality we need and how we can reuse the water. By the way, if we look at the paper industry, it seems that the value of economic activity per cubic meter of wastewater produced is the lowest for the paper industry, which is kind of surprising for me. Okay, let's look at the water intensive processes, because those water intensive industries are water intensive because they have water intensive processes. And this is more or less generic for many industries. Like this first one, steam production. Many industries still, also this time, use steam, but that's for different purposes. Cooling is a very water intensive process. Transport is an intensive process. Washing, of course, depends on the industry. In the food processing industry, but also in the chemical industry, there's a lot of cleaning in place, and so on. So there are many water intensive processes. Like here, to make 1 liter of beer, you need 1 liter of water, but you need more water. So that's for the cleaning and so on. So typically, well, when a brewery does a good job, it's 6 liters per liter of beer, but some breweries use 20 liters per liter of beer. So let's look at 2 examples: steam and cooling, steam production and cooling as 2 water-intensive processes. So steam is used for many purposes: propulsion, drive. So one example is electricity production, to drive a generator turbine, but also for heating and sterilization, motive, atomization, and so on. And here, drying. So, for example, in a paper mill, steam is used for drying the paper web. So many applications, many uses of steam, and typically for steam is we need a high quality feed water to make steam. We need heat, energy, and there's also a loss of water through water vapor, but also condensate. Cooling, that's another water-intensive process. So cooling, in fact, is needed to condensate steam. That's one application, but also condensate hot process gases, for example, in the chemical industry. So there are several types of cooling, and at the moment, there's some discussion about the cooling of data centers. So should they be water-based or should they be air-based? And that's a matter of the energy you can use, energy input. And so typical, why are we using water for cooling purposes? And the main reason is that water has a high enthalpy, as we call, of vaporization, which is that in 1 kilogram of water, you have to put in a lot of heat, a lot of energy to make steam. So the other way it also works. So when you have steam or a hot gas, then you can use water very efficiently to pick up the heat. This shows an example of the use of steam and cooling in the industry, and this is a typical example of a power generation plant. But this can be this is just one example, and it also holds for other examples. So steam is produced in a boiler, and then the steam is used to drive a generator in a turbine, and then we obtain some condensate. We need cooling to cool down the water vapor, the steam to water, and then we obtain a condensate, and then typically this condensate is fed back to the boiler. So we need some in this process. We have some accumulation of salts and all components that sits in the water. So at some point we need to bleed some water, what we call blow down, but to compensate for this blow down, but also to compensate for the loss of water through vapor. We need to add boiler makeup water of a high quality. On this side, we have the cooling. So that's also a loop. So the hot water that has picked up the heat from the condensate is cooled down in an evaporator system and cooling tower. And then the cool water is fed back to the heat exchanger. Also for this cycle, we have a blowdown because salts and minerals and components, they accumulate. And we need a makeup water to compensate for that. And also there's a loss of water through vapor. So in this scheme, we see already two, what you could call waste streams of different quality. They can be mixed and treated, but they can also be reused. And two makeup streams, and they are of different quality. For a boiler, we need high quality water, ultra pure water. For high pressure steam, even ultra pure water. The makeup water for the cooling tower, that's a bit less critical, but it needs to be a good quality as well. So, by the way, that steam generator can be any water intensive process in the industry, or many water intensive processes. So I mentioned already a few types of water. So we have many types of water within companies. So as we have seen already, we have boiler water, feed or makeup water. We have cooling tower water, feed or makeup water, but also the blowdown waters. We also have produced waters as a byproduct. In the sugar beet industry, for example, sugar beet contains 4 liters of water, and this is not used, and it's produced water, so it's a byproduct. But in some oil and gas petrochemical industries, there's also water production with a specific quality. We have processed water for all kinds of production processes and condensates, of course, ion exchange, regeneration, brines, but also membrane filtration processes. They create brines, concentrates, and so on. So this is a non-exhaustive list. So just as an example, this is, I got this from Tata Steel. That's a steel company in the Netherlands. And internally in the company, they have a lot of names for all the different water types they use. So they speak about A water, M water, G water, and so on. And they have all different qualities. I'm not going through this whole list, but it's very specific. But just to illustrate that in a company, a steel producing company, a lot of water is used first, but also they have a lot of different water types for different purposes, and also different residual waters with different qualities. And so in the steel industry, typically a lot of is used for cooling, but also big share for material conditioning and also air pollution control. As an example, this shows a simplified company with 3 processes. 2 processes use water. They are water intensive typically, and we have some feed water that are used in these 2 processes. And these 2 processes, they might produce a residual stream. One might be polluted, high concentrations of whatever, and the other one might be less polluted. And the general approach, conventional approach, is to mix these streams and then deal with it in a final industrial treatment plant. However, as you can imagine, we can also decide, okay, because this stream is not polluted, let's not mix these 2, because we can discharge this somewhere without any treatment. So then the advantage is that we can downscale this treatment plant, because we have less water to treat, and it's more concentrated, which makes it easier. But there are more options, like this low polluted water can be fed back to the first process, where we need a water that might not need that high quality. So that would mean that we would need less water intake. So that is on the front end an advantage. So you can imagine if you have 10 different processes or 20 different water intensive processes in an industry, then there are a lot of options to consider to save water intake and produce less residual water. This is an example of such a specific reuse scheme, what we call cascading. This is in a chemical plant. We have some water source, and this receives some treatment because it's not, even if it's reasonable quality, it might not be good enough for steam production. So we need to treat it to obtain a higher quality, and that's what we call the makeup water. This water is used in steam production, and this application of steam can produce a condensate with a lower quality. This condensate is still good enough to be used as a makeup water for cooling. After use in cooling, we have a cooling blowdown of a lower quality, but also this quality might be high enough to be used for pump flushing, a practice that is used a lot in the chemical industry. But after its use for pump flushing, then the quality is too low to be used for any other purpose, and then we call it residual water, or it can be wasted or worked up to some other use. So what are the technical challenges? If we look at most industries, most companies, to separate streams. So we need some, it can be very complicated, so we need some decision support. You can develop systems for that, and some attempts have been done. And one example is the water pinch analysis. We might also look at redesigning water-intensive processes. So you can operate these processes in a different way so that you can reduce their water use, but also their chemical use, so that the quality of the used water is different, is better. We can think of recycling, reuse, and cascading, but also when you reuse a lot of water, more brine, saline streams will be generated, and we need that's a big challenge to deal with brine handling, the brine handling, and because of we recover more and more water from those streams, we obtain more extreme streams. Brine is an example, but also highly organic streams or other saline organic streams. And as mentioned, brines and also condensates are produced. So I'd like to focus a little bit more on these two, brines and condensates, to give a few examples of our research. And this is an example of using residual brine from a desalination plant. So desalination plants, they produce brine because they extract minerals and salt from water to produce, for example, drinking water or dam water. And in this process, we try to use the brine, the residual brine, to produce concrete, and more specifically to use three-dimensional concrete printing. So, and this represents the desalination plant, and the next blue block represents the treatment technology. And this is, for example, we are looking at electrodialysis to optimize the brine. So we just optimize the brine to make it fit to be used as for two purposes in the concrete printing industry. And one is as an mixing water, and second, after transport to the printer, as an accelerator. Well, this picture shows a video of such a concrete printing using brine as mixing liquid and accelerator. And as you can see, you can print all kinds of structures this way. And well, depending on the brine quality, and that's the research here, it might also collapse because of the quality of the produced concrete, depending on the brine quality. So another example is also about brine, and that's a project, a European project, Zero Brine. So this is again an industrial desalination plant to produce different types of high purity water for the industry. It consists of an ion exchange to remove minerals and a reverse osmosis process to remove salts. So we have two brine streams, one for the first stage and the other one for the second stage. And we run two pilots, two sites. And in one pilot, and this is not optimization of brine to use for concrete printing. No, this is recovering minerals from this brine stream, and more specifically, calcium hydroxide and magnesium hydroxide. And with this, from the second stream, we recovered using sodium sulfate and sodium bicarbonate and sodium chloride. And this, more specifically, this sodium chloride was reused in the regeneration of the ion exchange resins of the first stage. This picture shows some of the recovered produced magnesium hydroxide and calcium hydroxide of a very reasonable purity. And of course, we used a lot of typical industrial water source extraction technologies, you can say, like evaporators, but also crystallization reactors and tactic freeze crystallization reactor and so on. So the second, just a few challenges about brine handling and treatment. So it's important to tweak production and the use and the treatment of the brine, because many brine is produced in batches, but the treatment process is not a batch, typically a batch process. Also, a kind of headache is the organics, and that are often present in brines for several reasons. Corrosion and scaling. On this picture, you see some pitting corrosion at these two pits at the inner side of a brine storage tank. That's a big problem. But also for brine treatment, we use typical chemical engineering technologies, but they are, not really designed for using the ill-defined waters we are faced with in the industry, used waters. The second example is about condensate. I have two examples about condensate, and one is a condensate from a fertilizer plant. It's a Norwegian plant in the Netherlands. And they produce fertilizers, and they produce a condensate which is contains ammonia, nitrogen, not surprisingly. And for the rest, this condensate is pretty pure, and it could be reused. It's a nice water source for different use purposes. And but the nitrogen, ammonia nitrogen, is a problem. And in this case, we had a 3-step treatment process to recover the ammonia. So in the first stage, the ammonia was concentrated to higher concentrations. In the second stage, the ammonia was converted to the ammonium effect in the water was converted to ammonia gas. And in the third stage, the ammonia gas was stripped from the water. The dissolved gas was stripped from the water. And this ammonia gas was fed to a fuel cell. And this is a picture of our lab fuel cell to produce electricity. And the electricity, at least most of the electricity, was used to run these processes. So the focus of the research is on the technical feasibility of a larger scale process and also the energetic performance. But it's a way to get rid of the ammonia or recover the ammonia, because, as you know, ammonia is a pollutant as well. This is the second example of a condensate treatment, and this was a condensate from bitumen, so asphalt, factory fume condensate. This is a condensate, no salts, no minerals whatsoever, but a high concentration of, well, volatile organic compounds. And these are just a few. There were hundreds of organic compounds in this condensate. And we used a biological reactor, a so-called anaerobic membrane bioreactor. So it's under anaerobic conditions to treat this condensate. And we achieved almost 90%, around 90% of removal, average removal of these organic compounds. So this is again with the purpose to recover that condensate, because this is a membrane bioreactor, and the water, the permeate of a membrane bioreactor, if you're able to remove the organics, then it's a high quality and fit for reuse, which is also the purpose in this asphalt factory. That's almost it. Well, first, what are the challenges around the treatment of condensate? So you can treat those condensates, as we've seen, physically, using physical technologies like electrodialysis or electrodialysis bipolar. But typically, the costs are very high and they use energy. And the biotreatment technologies, like the anaerobic membrane bioreactor, one challenge is membrane fouling, and that can also be a result of high salinity, but also a higher temperature. That's growth of microorganisms, for example. But also microorganisms are inhibited when certain organic compounds are present, but it's also inhibited by salinity. And these microorganisms grow very slowly, so it takes a while before you get a reactor that's able to remove those compounds. And also, especially when you treat condensates, there are no nutrients, so you need to add nutrients in the right proportion. And to finish, a few take-home messages. And when we look at water use in the industry and water reuse, we are looking at different process streams of the different processes, and we try to keep them separate, not to mix, to get a mixed, what you could call a wastewater, and so avoid wastewater production and reuse as much as possible. But it's important to understand the system dynamics. So just because of the production processes are kind of mingled with the water treatment processes, and this makes it very difficult to understand. Some processes are operated batch-wise and others are continuous, and so a good understanding of the system dynamics is needed. And also sensoring and control strategies, and that are new types of sensors and also newly developed control strategies dealing with the production process and the water recovery processes. We need to develop dedicated technologies to deal with those, for example, extreme streams. We need to take care of accumulation of constituents, because we can recycle water not forever, and there will be some accumulation, and we need to deal with that. And another important point is we need to think about how we can design the production processes. So that's the core business of most companies. That's the production and not the water treatment processes. But if you redesign these production processes, they might need less water or water of a different quality. That's my presentation, and I would welcome any question.